here. Okay, so if we look at example one, this is one of those getting our toes, just testing the waters kind of thing. It's always easy to do stuff graphically, but eventually we're going to be able to find everything that we're doing graphically just from the equation. Okay, so if you look at this right here, and I'm going to kind of combine a couple of things here. If we look at this on the closed interval, this function is continuous on the closed interval. We want to determine the extrema. Okay, so that might be all you're given, right? So when you read extrema, you have to realize, first of all, it means max and mins, right? And then you ask yourself, what type of max and mins? Local / relative or absolute / global? Well, because it's not required to say what type, when you mean absolute or global, it means absolute or global. So this is an easy one. Look on the closed interval from A to F. Do you see a Y value that is taller than all the others? Yeah, I do too, right here. So we would say that F of D is the max value, or just the max. And it occurs at X equals D, okay? If you want to write it in a sentence, we write it like this. F has a max of, well, I'll just leave it like that. We'll do it for the min, okay? And then is there an absolute minimum? Is there a Y value that's lower than all the rest? Yeah. Where does it occur? At A, right? Because I'm including the endpoints. If you notice, these are brackets. I actually have the Y value at the endpoint, and F of A is the lowest value. So we could also say then that F has a min of F of A at X equals A. All right. So whenever we say of, we're talking about the Y value. Whenever we say at, we're talking about the X value. Okay. So right there, you kind of get an idea of two different types of X values where these absolute extrema or global extrema or just extrema can occur. All right. If you notice right here at A, it's an endpoint of the interval. And if you notice at D, it's not an endpoint of the interval, it's on the interior, but we are in a calculus class. Is there anything particularly of interest regarding the derivative of this function at D? It's 0, right? It's a horizontal tangent line. What's the value of the derivative at A? We can tell, actually. It's continuous at A because we made that allowance for the two-sided definition of continuity at an endpoint, but we never said that about differentiability. So a derivative is never going to exist at an endpoint, ever. So the derivative there is undefined, okay? The derivative at F is also undefined. Is there any other place on the interior where the derivative is undefined? At C, right? So the derivative is undefined at A, C, and F, but the derivative is equal to 0 at B, D, and E, okay? And that's why those are the only points that are marked with vertical dotted lines, because those are really the only candidates, right? Would this guy right here, would this Y value, would he even have a shot at being the absolute maximum? No, poor guy, because there's Y values immediately to his right that are bigger. Poor guy. Could he be the absolute minimum, though? No, because immediately to his left, there's Y values that are lower. He's just a big nothing, right? He's not going to be the winner of the biggest or the smallest Y value contest. Now, I'm going to jump down and then come back up. I'm going to jump down to local extrema. Okay, so this is on page 4. Relative extrema or local extrema. Notice how that is not in parentheses. See that? That means it's required to say which type. If you want to talk about a local maximum, you better say local max or relative max. If you're talking about a local minimum, you better say local minimum or relative minimum. Otherwise, people are going to assume you're talking about the global absolute type. So what's the difference? Well, if there exists an open interval, and this is a hugely important thing, if on an open interval at some X value, if immediately to the left and right, you have values that are lower, then we call it a local maximum. And if you look immediately to the left and right, and you find values that are bigger, then it's a local minimum, okay? Now that's the litmus test definition, but for the most part, if it's a continuous function, you can determine it by just noticing hills and valleys, okay? So local, I tend to use local more than relative, but it works either way. Local max are essentially your hills, and local min are essentially your valleys for continuous function. They can actually be at discontinuities too, as long as the function is defined. So do we have any hills or valleys here? Well, yes, I have this hill and this hill, right? So what we could say is f of b is a local max, okay? He's not the absolute max, right? He's like not the tallest point in the whole wide world, but in this relatively small interval, right? That's where the word relative comes from, or on this local interval, right? If you zoomed in, he is the tallest, right? On this interval. And the litmus test again is if you go to this y value immediately to the left and immediately to the right, we find values that are lower. That's a local maximum, okay? Not the absolute max, but a local max, right? We have the highest point in New Braunfels, we have the highest point in Seguin, we have the highest point in San Marcos, but none of those are the highest point globally, right? It's right behind the HEB on Corinth. It's the old Corinth property, this West Point. If you look up there, you can see the highest point behind HEB is the highest point in New Braunfels. Yeah, used to be the old Corinth property, but yeah, it's a great view there. Do we have another local max? Well, is f of d, which is the absolute max, is he also the local max? Yeah, Mount Everest is not only the highest mountain in the world, it's also the highest mountain in Tibet, Nepal, right? Yeah, so f of d is the max, and it's also a local max. All right, do we have any local, is this a local max? How about right here? Let's look at this. No. Now, some people make an exception, but they're not math purists, right? Because those people would say, hey, in this local vicinity, there is no point higher than the right endpoint. But this is not going to be a local max because there's nothing immediately to the right. Okay, you look immediately to the left and you see values that are lower, but you can't look to the right. That's why local extrema have to occur on a through street, on an open interval, okay? On an open interval. So endpoints can be absolute max or mins, but they can't be local max or mins, okay? A little bit of a difference there. So can A then be a local minimum? No, it's an absolute minimum, but it's not a local minimum. Do we have any local minimums? Well, yes, right here, f of E is a, I'm going to use relative, is a relative min. And what about f of C? That works, right? Yeah, it works. Yeah, it works. Definitely. It's in the domain. It has to be in the domain, right? You're not going to say that, 10 feet above Mount Everest is the highest point in the USA, right? Because it's like you can't stand there, right? There's nothing there. It has to be in the domain. I don't know if that was a good analogy or not, but I was part of it. F of C is in the domain, and if you zoom in immediately to the left and right, you have values that are larger than it. F of C is a local min. Okay. So there you go. Now let's look at all the local extrema. What do you notice about the value of the derivative at every one of the local or relative extrema? It's either 0 or undefined. It's either 0 or undefined. Yes. Now, do you think every time the derivative is 0 or undefined, it's going to be a local max or min? No. You can easily look at like the graph of just x cubed. That looks like this. This is the graph of x cubed. Right there at the origin, you have a horizontal tangent line. But it's not a local max. because if you look immediately to the right, you have values that are bigger. It's not a local min, because if you look immediately to the left, you have values that are lower. It's not on a hill or a valley. We call it a stationary point, but what goes up doesn't necessarily have to come back down. What goes up can sometimes continue to go up. So it's still a candidate, right? It's possible. If we were looking for a way to algebraically find the local extrema, we would want to find where the values of the derivatives are 0 or undefined, but then we'd have to be able to test them to see if they were or not. So that kind of leads us to a very important definition. So right here, going right above the definition of local max or mins, okay? A critical value, also abbreviated as a CV, critical value. So critical outside the math classroom means very, very important, but in a math classroom, it's a term, right? It's a definition. So a critical value, first of all, is an X value in the domain of the function. It has to be in the domain where one of two things either happen. Either the derivative there is 0 or the derivative there is undefined. Okay, that's a critical value. If you throw in the ordered pair, C for critical value, comma F of C, you call that the critical point. It's an ordered pair. Okay, critical values become potential local extrema. CVs are potential locations, I should say, of local extrema. Now, as we already saw, not every critical value is going to end up being a local max or min, like on x cubed at the origin. But here's the theorem. If we do know a function has a local extrema, it's because, I'm looking at the wrong theorem here. Where is the theorem I'm looking for? Did I miss it? Oh, yeah, that's a different theorem. Let's, oh, here it is. Yeah, it is right below it. Duh. Relative or local extrema, thank you. Yeah, can only occur at a critical value, only on an open interval. I'll just throw that in there again. Can't be an endpoint. Why do I throw that in there? Well, let's come back up here again to this example. Would x equals a technically be a critical value? Yes. Is it in the domain? Yep, there's a dot there. What's the value of the derivative there? Undefined, DNE. So it is a critical value, but it doesn't have a shot at being a local max or min because it's at an endpoint. Okay. So local extrema can only occur at critical values on an open interval. All right. So already we've got some terminology. I'm trying to see what's the best way to do this. Okay. I'm going to skip the EVT for just a second. Let's talk about absolute extrema then. This is the other theorem. Absolute extrema, global extrema, can occur at one of two places. They can occur at a critical value on the interior. I'm going to go ahead and say on the interior, or at an endpoint, right? Which is also going to be technically a critical value. It's a special critical value that can't be a local extrema, but it can be an absolute extrema. Okay. All right. So what we want to figure out now is, when are we going to be guaranteed to have an absolute max or min? When are we going to be guaranteed to have a global max and a global min? That brings us to the EVT. Okay, I know I'm jumping around, but I wanted to introduce the local extrema to you earlier than I have in the notes. All right, so we've already had the IVT, right, which is the chicken crossing the road scenario. The EVT is called the extreme value theorem, and by extreme value we mean extreme Y value theorem. Extreme Y value theorem. And it deals with absolute extrema. Absolute global extrema. Remember, you don't have to say global or absolute. So when we say extreme value, by default, we're implying absolute or global. Bless you. Now, look what the if part is. If f is continuous on a closed interval, that's it. Does that ring a bell? Yeah, what's the if part to the IVT? On a closed interval from A to B. Yeah, it's the exact same thing. So not only then, if a function is continuous on a closed interval, not only will it take on all the y values in between the y values of the endpoints, like the IVT says, but this is going to happen. Then f is guaranteed to have both a maximum value and a minimum value on the closed interval, right? It could be an endpoint, could be at A or B, or it could be on the interior. So when are we going to be guaranteed to have both a max and a min? When the function's continuous on the closed interval. Okay, so again, retreating to this little graph up here, this function was continuous on the closed interval. Did we have an absolute max? Yep. Did we have an absolute min? Yep, we did. Okay. Now, could you have an absolute max and min occurring when it's not continuous on a closed interval? Yes, there's just no guarantee. All right. So if you look at some other examples here, here's another graph that's continuous on a closed interval. We have an absolute max and we have an absolute min. Okay. In this case, they're both occurring at the critical values on the interior where the derivative is 0. Here's another function that's continuous on a closed interval. It has an absolute max on the interior at the critical value C, and it has an absolute min at the critical value that's an endpoint. And then here's one that Ethan was all over before lunch, like a bag of Doritos at lunch in his hands, I guess. Yeah. This function's continuous on the closed interval from A to B. Does it have an absolute min? Yep, it occurs at the interior at x equals d. Does it have an absolute maximum? By the theorem, it has to. Are there two absolute maximums? No. No, there's only one absolute maximum. Because the absolute maximum is an x value or a y value? It's a y value. And these have the exact same y value. And that one y value that occurs in two different places is bigger than any other y value on the interval. So that's why it's important to realize that the maximum values are the y values and they occur at x values. So like you can have an absolute maximum temperature in a 24-hour period, right? The maximum temperature for the given day was 70 degrees. Could that maximum temperature occur more than once during the day? Yeah, right? Sure can. So that's the idea here. So there's one maximum value that occurs at two different places, and they're both at interior critical values. All right. Now, the EVT applies for each of the function. If the EVT applies, find the extrema. If not, let's say why the EVT doesn't apply, and then determine if it still happens to have absolute extrema. All right, so here's a function. These are all going to be f of x's. They're all going to be on the interval from 0 to 2. Does the EVT apply to this function on the interval from 0 to 2? No. See, so you have to when you're given a name of a theorem, you have to know the if part. And we would say no, EVT does not apply because what? F is not continuous. And we want to say specifically, we'll say at x equals 1. And why is 1 important? Because look at this, epsilon, it's on the interval from 0 to 2. So does the EVT apply? No. No, it doesn't. Could it still have a max and or a min? Yeah, sure can. No guarantees though. Does it still happen to have an absolute minimum? Yes. Okay. The minimum is what? 0. Good. I'm going to put y equals 0 at x equals 2, the right endpoint. Does it have an absolute maximum value? You don't know so. No, I don't know. I know so. I'm sorry. You do know so. because this is an open circle up here, we can get infinitely close to 3 from underneath without hitting a high point. 2.9, 2.999, 2.9. No. Okay. So EVT doesn't apply. Now, because we already know about local extrema, let's see if this function has any local extrema at any points from 0 to 2. It can't be at 0, can't be at 2. Those are endpoints. Is there any other critical value between 0 and 2? Because local extrema can only occur at critical values. Is 1 a critical value? Yeah, let's see why. You're right. Is it in the domain? F of 1. Yeah, it's in the range. Sorry. 1 is in the domain because there's a dot. And what's the value of the derivative there?
It does not exist.
Why? You're right. Because not continuous. Any place where a function is not continuous is not differentiable. So yes, in fact, x equals 1 is a critical value. So on the closed interval, this function technically has 3 critical values, 0, 1, and 2. On the open interval from 0 to 2, it only has the 1 critical value at 1. Do we have a local max or min at x equals 1? No, because if you go to the y value, immediately to the left, you have values that are bigger. And immediately to the right, you have values that are smaller. So it's critical value, but not a local max or min. Okay, bigger on this side, smaller on that side. So we'll say no local extrema. All right. Letter B. Does the EVT apply to this guy? No. Okay, because F is not continuous at either endpoint, right? It's continuous on the interior, but it's not continuous at either endpoint. So the EVT doesn't apply. But it still could have both the max and a min, or one of each, or neither. Does it happen to have a maximum value?
Oh, shoot. I would say yes.
Really? This is a vertical asymptote. The arrow means going up forever. No, there's no maximum. No global maximum value. No absolute maximum value. No max value. All mean the same thing. Does it have a global min? An absolute min? A min? No. Yeah. For the same reason the other one didn't have an absolute max, this one is decreasing, getting closer and closer to 1 from above, but there's no lowest single number, 1.01, 1.001. So this one actually has no extrema. And again, that's plural for absolute max, absolute mins. Does this function have any critical values? No, none at all. Are the endpoints critical values this time? They're not, because they're not in the domain. So the endpoints aren't even critical values. Do we have any places on the interior where there's a horizontal tangent or a sharp turn or a discontinuity? No. So no critical values. If there are no critical values, do we even need to look for local extrema? No, because local extrema only occur at critical values. So not only does it have no extrema, it has no local extrema. And that's answering 2 different questions. Okay. Sorry, graph. Sorry. I didn't want any extrema anyway. Which type, sir? Yeah, thank you, Brian. EVT applies, yes or no? No, it's continuous at the endpoints, but it's not continuous again at 1. No, not continuous at x equals 1, which is in the interior from 0 to 2. Does it happen to have an absolute maximum regardless? Yes, it does, right? We have a max of y equals 3 at x equals 2. X equals 2 is the right endpoint. It's also a critical value. Okay. Do we happen to have a minimum value? Yes, it's this one here. We have a minimum of, I guess I could say 1/2, but I'm not sure. So I'm just going to say f of 0 at x equals 0. So we still have a max and we still have a min, even though the EVT doesn't apply. No guarantee. We just got lucky, right? All right. Do we have any other critical values besides the endpoints here from 0 to 2?
Yes.
Yes, there is a critical value at 1 because, again, A, it's in the domain. I see a dot. And 2, it's not continuous. Therefore, it's not differentiable. So that is a critical value. Is then f of 1 a local max or local min? No. To the left, we have lower. To the right, we have higher. So no local extrema. But we do have 3 critical values on the closed interval and just the 1 critical value on the open interval. Sometimes you have to read very carefully because it might ask you that question. How many critical values does this function have on the closed interval from 0 to 2, which would be 3? Or it might say, how many critical values does the function have on the open interval, which means we don't care about the endpoints. All right. And then last dude here, EVT apply, yes or no? No, not continuous, again, at either endpoint. Not continuous. Do we have any critical values?